Okay, so now we're getting into a new law. And so the new law is called Avogadro's law. It's actually pretty easy to understand, and the reason is because we do this quite a bit in our lives. We have seen examples of Avogadro's law by blowing up a balloon. So imagine that you have a balloon that's just out of the package and is relatively deflated. Now you know that balloon will have a little bit of air inside of it. That air in that deflated balloon causes the balloon to have a certain size, and so it has a certain volume. Now, you know if you blow up the balloon, you're basically taking the amount of air that is inside there, which is a certain number of moles, and you're just adding more moles to it. When the moles of air in that balloon increase, then the volume also increases. And so this will happen as long as the temperature is kept constant and the pressure remains constant. And so this is sort of basically Avogadro's rule, is that when you have some kind of flexible container that can hold a gas, if you increase the number of molecules or the number of moles in that container, you're going to have to increase the volume of that container as long as you keep temperature and pressure of the gas constant. So in a sense, what you can sort of see is that as the number of moles of the gas increases, the volume of the gas increases. And so what that says is that the number of moles is directly proportional to the volume of the gas. And so what we can do is we can write that in a pretty simple equation that V is proportional to N. Now, what you might remember is if you wanted to, you can turn that equation into an equality as long as you add some kind of numerical constant. So if V is proportional to N, you can also write V is equal to a constant K times N. And then if you wanted to, you could solve for the constant K. If you wanted to, you can sort of derive an equation from that. So that'll be V1 over N1 is equal to V2 over N2. And again, this only really applies if the pressure and the temperature are constant between these two conditions of 1 and 2. So again, this is Avogadro's law that if the number of moles of a gas increases, that the volume increases. I kind of just talked about this a moment ago, the explanation as to why there is Avogadro's law. And again, as you know, that when you increase the number of molecules or moles of a gas in a container, its volume must proportionally increase if the pressure and temperature stay the same. So let's go ahead and try a problem using this relationship. And it says, let's say you have a large balloon with 0.35 moles of gas that has a volume of 8.56 liters at 25 degrees Celsius and 1 atmosphere pressure. If you were to add 1.0 mole of gas to this and the temperature and the pressure remain the same, what is the new volume? So let's go ahead and see if we can solve this problem here. So let me just write out what the initial conditions are. So here we're given an initial number of moles of gas, which is 0.35 mole. And we're also given an initial volume. V1 is equal to 8.56 liters. Now, just a note, we're also given a temperature and a pressure. So let me go ahead and write this here for the moment. So the temperature is 25 degrees C, and the pressure is at 1 atmosphere. Okay, this says, if you were to add 1 mole of gas and the temperature and the pressure remain the same, what is the new volume? So we have new conditions where we're adding a mole to the gas that we already have 0.35 moles of. So N2, after you add that mole to the original number of moles that is there, we should have 1.35 moles of gas for N2. So what we're trying to do is find the new volume that this gas occupies now after it receives another mole of gas. But the temperature and the pressure in these new conditions is the same as it was in the original conditions. And so if that's the case, we don't have to really worry about that in the problem. So we can just erase that. And so if we know a relationship between moles and volume, we can figure out what the answer to the problem is. And that relationship is Avogadro's law. So we again know that the moles of a gas at initial condition divided by the volume of the gas at that initial condition is going to be equal to the moles of the gas at the final condition divided by the volume at the final condition. And so what you can do is solve this equation for V2. To do that, I'm going to move V2 to the other side of the equal sign here. And so I have V2 is equal to N1 over V1 is equal to N2. And so I need to get V2 by itself. And so to do that, I have to move N1 and V1 to the other side of the equal sign. So V1 in the denominator here goes in the numerator. N1 in the numerator here goes in the denominator. And so I get V2 is equal to N2 times V1 over N1. I think that's probably correct. What we can do is go ahead and plug in numbers. And so V2 is equal to N2, which is 1.35 mole, times V1, which is 8.56 liters, over, and it looks like N1, which is 0.35 mole. So what I'm kind of hoping we'll see is that you can sort of look qualitatively at this problem, that if we're adding moles of gas to the gas that's already there, we would expect the volume to increase. So let's just hope that we get out an answer that is larger than the original volume of 8.56 liters. So let's see, it's 1.35 times 8.56 divided by 0.35, and I get 33 liters. So yay! So that is consistent with what we would expect, that when you increase the moles of the gas holding the pressure and temperature constant, that we would expect the volume to increase, and that's what happens. So that appears to be the correct answer. So we will move on. Another thing you sort of need to understand is you're going to see problems where you may have to take a gas at initial conditions and then figure out what a property of the gas is at something called standard conditions. And so standard conditions are a particular pressure and a particular temperature. And so at standard conditions, the pressure of the gas must be average atmospheric pressure, which is 1.0 atmosphere, which is 760 millimeters of mercury. And the standard temperature would be 0 degrees Celsius, which is 273.15 degrees Kelvin. Now, another thing that's kind of useful to know is you should understand what volume any gas occupies if you have 1 mole of it at these standard conditions, meaning you have 1 atmosphere pressure and 0 degrees Celsius. It's always the same volume no matter what gas you have. At standard temperature and pressure, 1 mole of any kind of gas, it could be oxygen, nitrogen, a mixture of gases, it doesn't matter. 1 mole of any gas occupies 22.414 liters of space. Now again to note, 1 mole will occupy that particular volume only at standard temperature and pressure. So for example, let's say you were to increase the temperature of that gas. And so 1 mole would occupy 22.414 liters of space at 0 degrees Celsius. But you remember from Charles' law that if you increase the temperature, you're going to increase the volume. So for example, if you were to double the temperature in Kelvin, you would double the volume. And so that 1 mole of gas would no longer be 22.414 liters. It would be a much greater volume. So again, this number, 22.414 liters of volume, only applies for 1 mole of gas when it's at its standard conditions of pressure and temperature.